8.10 Buffer Capacity. Our outcome is I can explain the relationship between buffering capacity of a solution and the relative concentrations of the conjugate acid and conjugate base components of the solution. So here we're looking at how we can design a buffer to make sure that it's able to withstand a certain amount of acid or base being added to the buffer without the pH changing. So buffer capacity is generally considered to be the moles of acid or base necessary to change the pH of a solution by 1, divided by the pH change in the volume of buffer in liters. So it's really a unitless number here. It really represents how much H plus or OH minus the buffer can absorb without a significant change in pH. So the buffer capacity depends on how much of my weak acid and weak base components are used, whereas the pH depends on this ratio. And so a good example here, this is a buffer that is made from acetic acid, a weak acid here. So when we do the negative log of this 1.8 times 10 to the negative 5, this gives me a pH of 4.72. So then whenever we do the log of this ratio here, that's the ratio of acid to base in my buffer solution. So whenever I do that here, I get negative 0.1249, blah, blah, blah. So this piece right here, this ratio, is what dictates the pH of my buffer system. How much of that is present dictates my buffer capacity. So a chemist needs a buffer with a pH of 4.3, and we can choose from the following acid-base pairs. So chloroacetic acid and sodium acetate, propanoic acid and sodium propionate, benzoic acid and sodium benzoate, hypochlorous acid and sodium hypochlorite. So we want to first calculate the pKa for each acid. So pKa, that P just means negative log of. So I want the negative log of Ka for all of these values. So when I type this into my calculator, here's what I get for my different pKa values. Now, given that our goal is to make a buffer with a pH of 4.30, we want to choose the weak acid and conjugate base system that is closest to that. So that's going to be our benzoic acid and sodium benzoate here. Now, this buffer that we're going to create here needs to be able to withstand the addition of 10 milliliters of 0.1 molar HCl and 10 milliliters of 0.1 molar NaOH. So I just need to figure out how many moles of acid it needs to be able to neutralize. So if I have 10 milliliters of 0.10 molar HCl, that's going to give me a total of 1 millimole of HCl. Now, my weak acid that we've chosen, benzoic acid, these are all monoprotic acids, which means the ratio of HCl to sodium benzoate here is going to be 1 to 1. So if I have 1 millimole of HCl, I'm going to need at least 1 millimole of my weak base here, which is going to be the sodium benzoate. Now, if I have 10 milliliters of 0.1 molar NaOH, that's going to give me, again, 1 millimole of NaOH. And given that the stoichiometry is 1 to 1 here, that means that in order to neutralize that amount of NaOH, I need at least 1 millimole of benzoic acid. So this is our buffer capacity here. We want to make sure that the buffer has enough weak acid and enough weak base that it can neutralize the addition of this HCl or NaOH without having major changes to the pH. So now we want to use our Henderson-Hasselbalch equation to solve for the ratio of base to acid to give the exact desired pH. So we know the equation pH is equal to pKa plus the log of base over acid. So these concentrations here. So we know that we want to make a buffer that has a pH of 4.3. So 4.3 is going to be equal to the pKa of the acid that we've selected. And since we've selected benzoic acid, my pKa we've already calculated is 1.49. So I'm going to put log, and I'm just going to put x here, because what I'm really solving for is what ratio of base to acid do I need in order to adjust this 4.19 to the 4.30 that we're looking for here. So I can do a little bit of math here, and I get this guy upon subtracting, and that is equal to the log of x. So in order to cancel out a log, we need to do the anti-log. So I'm going to raise both of these to the 10th power. So that will cancel out the log and leave me with x is equal to 10 to the 0.11, which whenever we type in our calculator, we get 1.29. So this is the ratio of acid to base. In order to have the correct pH, I need the ratio of those concentrations to be 1.29. Now remember that this 1.29, this ratio, is equal to the concentration of base over the concentration of acid here. So this is just telling me that the concentration of base needs to be 1.29 times the concentration of acid. So from our previous calculations, we need 1.29 times more base than acid. So from our previous calculations here, if we were going to make, say, a liter of solution here, I know that I need at least 1 millimole of each of these. So I would need 1 millimole of my benzoic acid, and I'm going to need 1.29 millimoles of my sodium benzoate. So the ratio of acid to base allows us to adjust the pH of the buffer, and the amount of acid and base allows us to determine the strength of the buffer, how much acid or base it's able to neutralize its buffer capacity. So does this buffer have a greater capacity for neutralizing acids or bases? It's going to be better at neutralizing acid because this buffer is going to have 1.29 times more base than acid. So that means that since this buffer has a larger amount of base in it, it's going to be better at neutralizing acids. So then what if my buffer needs to withstand 100 milliliters of 0.1 molar NaOH and HCl? So if I have 100 milliliters of 0.01 acid or base, my concentration here, that's going to give me 10 millimoles. So this buffer needs at least 10 millimoles of my weak acid and weak base. So 10 millimoles of each of those is what we need here. So I still want my buffer to have a pH of 4.3. So I still need 1.29 times more base than acid. That way my buffer will have the correct pH. So based on that, I'm going to need 10 millimoles of my benzoic acid. And I'm going to need 12.9 millimoles of my sodium benzoate. So for your reflection questions here, buffer capacity depends on the magnitudes of A minus and HA, and the pH depends on the ratio of HA over A minus. Explain. A buffer system is made from half a mole of weak acid and 0.6 moles of its conjugate base. Will this be better at neutralizing acid or base, and why?